Welcome to our talk, Intro to Reactive Programming. A little bit about ourselves. I am Rossen, and I am a Spring Framework committer. I work on Spring MVC, generally web topics, WebSocket, the WebSocket support in Spring. And for me, this is a new topic. So my role in this presentation is basically to check what Stefan knows. He's the expert on the subject, and make sure that we break this down in a way that you guys can follow and understand. In general, this is a forward-looking topic. It's very much a fundamental change to the way we think and the way we do things. And I don't want necessarily everybody to think that you gotta leave this room and go change everything that you do, but it's definitely something that you want to start looking at and something you want to learn about, which is why we have this presentation. And this is Stefan.
Hey, actually I'm going to step away, like very away. So I'm the Reactive project lead, and I'm a contributor to a specification we're going to talk about in this talk, actually, called Reactive Streams. And I'm glad actually I'm presenting this with Rossen, because even if it said I was like expert, it's not really the case. I learn every day, and it translated all my bullshit into something I hope people can get, and yes, we'll see if that works out.
So if you're not the expert, then we have no chance.
Yeah, everyone is going to learn anyway. I think I'm going to learn new things, even talking.
All right. Now we have quite a bit of content, and we're going to see how we fit in the time slot. It's a very, very big subject, but we really don't want to rush through it. So we have a good slide deck. If we have a few more slides left at the end, basically we'll stop where we are, and we'll take some questions. Just want to set some expectations that it's a big subject, and anything we learn here, that's the goal. So with that, first we're going to open up with talking about motivation. What is the context in which we're talking about reactive programming? Then we will define reactive programming. We will try to put a summary and a definition. And this is something which you won't see too much of out there. There's a lot of different angles and ways in which it's explained, but we're really trying to provide as good a definition as we can come up with. And then we're going to go more into the details and show you specific things that you can do and specific tools.
All right. Right. So, where are we today? We know that concurrent programming has been around for quite a long time, and we know the basic rule, also the Moore law, for quite a long time as well. And we know that at some point, we're not getting faster, we're just multiplying the number of cores. But that at some point we're going to reach a plateau where we're not getting even more performances from multiplying the number of cores. And that's because your CPUs are going to spread the focus. Spreading the focus means, well, a concurrent handoff is going to be quite difficult and overwhelming for all the CPUs. So at some point, multiplying the number of cores is not getting you better performances. So,
who has read this book? How many have read this book? Right. So this is back in 2006, and that's when we had this forward-looking revelation that concurrency is going to become a major part of what we do. But if you think about it, I mean, things haven't changed all that much for what we do, and in some ways we're living a little bit on borrowed time, and we're going to talk about some of the things that have happened since then.
All right.
It seems a little hard.
Yeah. So, a new law has kind of emerged, especially has been really advocated by a few, and especially a few manifestos around, and it's called the Amdahl law. Basically, you can try to multiply your number of CPU, your number of parallel computing, but you're going to reach a plateau because the sequential the sequential processing is getting in between you and actually the performances you're trying to reach. And what does it just means is at some point, any blocking code you're going to have, and we're going to define what's really blocking and non-blocking a bit later, but any blocking code is going to impact evenly really the concurrency and the performances you get from concurrency in your application, Java or not. So, So why do we try actually to speak about concurrency and scaling? Well, if you remember SOA, AGB, we already started talking about distributed components and transparently scale, transparently also, which was a kind of a mistake, try to scale processing by abstracting away the invocation on some remote objects. But the problem with that is the boundary were not clearly defined. You didn't really know when you switched to a remote call or not. And that's probably the biggest thing you need to remember after this talk. Crossing a boundary, either a network boundary or a thread or an asynchronous boundary, is super costly. If you don't know in advance, if you don't see explicitly this crossing happening, well, it's just putting a string of issues, and that's why actually that failed.
Yeah, it was a little too fine-grained, right? To promise that a component, any method is suddenly going to run on any computer and is going to cross a boundary. And I think Martin Fowler had a phrase that he coined that was famous, where he said that you should sell your favorite grandmother first before you go for distributed objects. SOA, kind of tried to change the granularity of things, but maybe it wasn't the right time. Maybe it was just a little bit ahead of its time. So let's take a look at some of the things coming up next.
And we had this kind of transformation back like now in 2015. So in 2008, 2007, the explosion of social sites, well, the explosion of traffic in internet, which required a new kind of processing handling for the massive web scale sites like, well, Facebook, MySpace. By this time, it was still alive. That was a kind of shift in paradigm, and one of the biggest things, actually Twitter wrote about that, one of the biggest solutions to scale and give the opportunity to have a low latency, fast response, quite a responsive site to users, was to actually defer the right with background processing. Like you tweet, it's not going to be synchronous, it's going to be handled by a different thread because you want a response back as a user quickly. You want just to see your action has done something on the server.
And we have cloud.
And then we exploded even more a few years before with the emergence of this open source path, one I know quite well, and the explosion certainly of AWS did something for all of this architecture.
And it doesn't stop there.
It doesn't stop there, actually. And now we're living a new boom in traffic with IoT. We inserted a Gartner graph, but we see there is actually a plan for massive explosion, another order of magnitude in terms of internet traffic. And we need to cope with that. We really need to change our thinking about how we program our application, Java or not. And that's also why popular new frameworks like Go or Node.js take over, because well, that's definitely the kind of architecture implemented by this framework when we talk about reactive programming.
Yeah, and it's not something that everybody has to deal with today. I mean, this is certainly worth making clear, but you can certainly see that those who are in that space, they have to deal with these very large, massive scalability questions, and the architecture that we know, the way that we've been scaling so far, simply doesn't address these kinds of problems and these kinds of issues, and something more fundamental is needed for that.
So, of course, there is still the ability to scale out, but if you remind the Moore law, which was about spreading the focus. At some point, you reach a plateau when you spread the processing, because the cost of handling the task to many processors is going to be reversed by handling to different processors, basically. That's the same for scaling out. If you have more than X number of nodes, unless you have a pyramidal scheme of load balancer behind, it's not going to buy you any more performances. At some point, you're going to reach a plateau as well. So another issue came with this kind of architecture. The memory is often overused because we use large pool of thread, and the threading model, until very recently at least, in the JVM wasn't great, for instance. We used to have this kind of pool of 100 thread in Tomcat, for instance, or JBoss, etc. And the funny thing is, where the memory was super used, or is still super used, because a lot of these applications are like that today, the CPU still is underused. If you look at the top of your servers, you see that actually you're still around 10, 20%. You're never going to reach actually the maximum, the 100% of your CPU. And that's because basically some of this is due to your application waiting to do something, basically sleeping. That's what we call blocking code. Every time you call blocking database driver, so a query to something, you're waiting, and the CPU is pausing, basically, and the system schedule again another thing to, well, even if there is nothing else to do, it's going to just wait for the response back while you don't do anything, you don't use your CPU.
Yeah, and again, back on the point about scaling out, there's a lot that can be done for many, many applications by simply having more instances of the application. There's no question about that. This is not to say that, if that's something that you apply today, that it's not valid. You can actually, go pretty far that way. The point is that there's a lot of benefit to be gained by considering alternative approaches. And certainly if you're in that space, if you're really pushing the boundary, you already find yourself looking for different approaches.
And actually, well, the core issue with scaling and specifically scaling out or distributed system is basically the physical law, the reality. Reality check, everything we do today is limited by speed of light. So this speed of light has a different cost actually if you reach a different host, or if you reach, everyone knows the Google programming, the programmer's number done by Google. So there is an order of magnitude difference between querying the local cache or querying a different host. And when you scale out, basically, or when you have a distributed system, this latency and introduced by the speed of light actually issue is what is going to slow you down at some point. You're going to pay this cost too much. Where if you collocate this processing actually and make a smarter use of the CPU in a single machine or in a single VM actually, you might try to avoid, or you might have a benefit to avoid some of this speed of light issue.
So we're looking at non-blocking as something that needs to be embraced fundamentally. And non-blocking is actually a very profound and deep change in applications. You really can't write code in imperative style anymore. You have to expect that something is going to call you back when it's finished, when it's complete, and that becomes the way that you do things to reap the benefits. You can't assume a single thread of control, so exception handling changes. If something goes wrong, it's not necessarily in the same call stack. And you need to deal with async results, and if you've dealt with that, you know that that becomes quite nested very quickly. So we need solutions for that problem as well. And yeah, just to kind of make it more real, if you think about using input-output stream, our I/O abstractions for blocking I/O, that basically now becomes a stream of events. Wherever you're using an input stream, you can't just block and wait until it gives you everything. You now have to be prepared to come back in another thread and continue dealing with that input or output. And this is really a very fundamental deep change that has to happen in order to be able to do this. And it's not easy, and it's not simple to introduce into an existing application. Just think about everything that's doing output stream .write. And actually, it's kind of interesting that it was a single-threaded platform that had to show us what can be done with a single thread. And I'm talking about Node, as you all know, which showed new levels of scalability with a single thread. So that's kind of the context in which we're going to define reactive programming.
So, interestingly, well, reactive has a few, depending on the angle, reactive has got a few different definitions over the past year. I think the common origin for reactive programming is the reactive term, actually, is kind of akin to the observer pattern, which was specifically done for reacting to UI events, basically a callback when you click, you have a mouse click or you have something happening. That was kind of the origin, so nothing to do necessarily with well, scaling or this kind of issue. But as far as we go back in time to the reactive programming origin or the reactive term, that's what you can find out actually.
Network protocols also very much constantly dealing with
yes.
Events. Basically, something comes in and you have to react and do something with it.
Exactly. And while this was the case, now over the past few years, the definition has quietly increased in scope, and this has actually got into the application logic, and we have seen the emergence of a new concurrency tool like the Akka stack, for instance, or if we think about the Vertex stack from Red Hat and other stack we're going to discover as well. I said probably yesterday in a tweet, I'm not going to have a slide.
I did that after your tweet.
Yeah.
I was not aware of it.
So yeah, it's not, so there is a definition around now called the Reactive Manifesto. And the Reactive Manifesto is nicely explaining things around reactive systems, which is kind of on a higher level than reactive programming. It explains the paradigm and how you could do that, or the vision of reactive systems in general, but it doesn't explain necessarily how does it work well, concretely, or in your code or in the language, for instance.
It's like a TV show that tells you how you need to be successful, but it doesn't tell you how to get there.
Exactly, with a smile. And that's exactly what's happening. But it's explaining that well, so kudos to that explanation. It's explaining the context well, but doesn't explain more than that.
So it's more about qualities of systems, where you want to end up, but for reactive programming, we need something more concrete. We need some kind of tools that we can see and use so we can imagine what we can do with that.
So what we have observed, actually we learned a lot also when we prepared this with the experience of the talk preparation. We have really observed that there are two domains we find in the reactive programming. There is one specifically bound to the message passing, and components that actually deal with asynchronous boundaries. And there is one which is more about composing asynchronous results. So there are kind of two domains, and this thinking is going to actually heavily influence the way we think even over the next milestone for Spring. If we talk about the reactive story for Spring, this kind of two categories, message passing and composition, it's really something we want to emphasize as well. And that's probably, even if you see this talk, it's going to probably divide in kind of two, this topic, message passing and composition.
Yeah, I mean, if we imagine a world in which our database driver and the data layer libraries provided some kind of non-blocking behavior, and we wanted to work with that, and maybe our web server as well exposes non-blocking behavior through and through, you need some kind of a API for these components to talk to each other. You need some way that they can do message passing, and that's what Reactive Stream specification that we'll talk about focuses on, to be that basically API and that mechanism. And then at the same time, you need something to rise above the level of callback mechanics. When you start dealing with events coming at you, you need some sort of a composition API for composing asynchronous logic, because you're no longer imperatively saying this should happen first, this should happen second, third, and so on. Now you need to compose asynchronous logic, and using callbacks is too low level, and it's not the right way to deal with it. And I guess it's useful to talk about myths about reactive, because reactive has become a bit of a hype word. So we'll mention a few things. Well, the first one is, I guess, asynchronous and concurrent is not the same as reactive. There are certain people out there that will claim that something is reactive when they actually mean asynchronous or concurrent. So that's one very big thing that we've heard to be said out there, which is not quite accurate. You must be async to be reactive. You don't really have to be asynchronous. In fact, the reactive stream specs specifically says and allows synchronicity in places. So it's really about being agnostic to how something is done, so that it can be synchronous or it can be asynchronous. But you don't want it to be imperative, basically, is the bottom line. But whether it's synchronous or not, that's a separate question. Doesn't have to be always async.
Specifically, if you start getting concurrency with a pool of threads, for instance, you know that if you do message passing with different threads, you're going to have probably a queue in between you and the new thread. And the new thread is going to read off the queue to process the new task. This has its own limitation, which Reactive Streams is trying to solve actively. The limitation of that is if your consumer is slow, basically, and your publisher is faster than your consumer, well, you know what's going to happen. You're going to have your queue in the middle that's just going to grow. It's not even a kind of memory leak or whatever. It's completely normal behavior. But you're going to have this increasing backlog of stuff because, well, the consumer doesn't do anything, and doesn't actively prevent that. It just tries to process the task as much as it can, but you know it's still slower than the publisher. It's maybe performing an insert in database or something like that, while the publisher is probably reading off fast message broker or request or whatever, maybe something faster anyway than the consumer. So another kind of myth as well, reactive is not really something bound to a specific language or programming language. So, well, I'm thinking specifically about one, and I guess people knowing this space or slightly hearing about this space know about what I'm thinking about. But GDK 8, for instance, offers some facilities, and there are, of course, facilities which help you to deal with reactive programming. You don't need to switch to another language. You don't have to implement, for instance, your application in Clojure or in Scala or this kind of functional programming language. There are some features you need, but you don't need a complete shift to a different programming language.
You don't technically even need Java 8. You can do
technically,
it.
No,
it helps.
But it helps. It makes things easier and smooth and more elegant, but it's not a requirement.
So basically, for the rest of the talk, we're going to roughly split it into two. First, we're going to talk about the reactive streams specification, which Stefan here was part of creating that specification. So that's why I call him the expert. That's going to focus on message passing. And then the second part, we're going to talk about composition APIs. And we're going to talk more about how this looks from an application perspective. So this is kind of like the low-level stuff that happens, which is very crucial and important. But then we'll talk about the composition, asynchronous composition APIs as well.
So Reactive Streams is a collaboration born, I think, early last year in January, between a few companies. I think we have explicitly a list after, I can't remember actually. But this collaboration led to, enough of all this definition of reactive, basically. We should align to something to define what exactly means being a reactive component, what means reactive message passing, basically. And that's exactly the focus of Reactive Streams. It doesn't focus on anything like API to compose, etc. We'll see that, but teasing a bit, if you have already seen that before, the thing like map, flat map, etc., it doesn't expose this kind of thing. It just exposes a way to say, I'm going to pass message from thread A to thread B. And we'll see also it supports synchronous calls, so thread A to thread A, but still in a protected way. And what means protected way? It just means that Reactive Streams is here to protect a publisher, so an emitting source of stuff, from slow or failing consumer. And that's the most important thing about this spec. It just helps you to have publisher keeping publishing while consumer can be slow or maybe fail. So it offers both a kind of resilience against this slow consumer, or it also offers a kind of way to scale and keep reading incoming events while the consumer is still slow to a limit.
And just to put it in context, so let's say you may have a Mongo or Couchbase data, and in order to work in a non-blocking way, we need some sort of contract to kind of pull data as we can process it. And if that data is just pushed at us and it's coming too fast, then we're not able to process it, and then we have to queue it, we have to buffer. So those are the kinds of issues that you begin to deal with in an event-driven application. And that's really what this specification is about. It's about defining what happens at an asynchronous or at a boundary between two non-blocking components and how they can pass messages to each other in such a way that, if possible, they can do it in kind of on an opt-in basis. So you can say, yeah, give me more. Yes, here's more, instead of here. But as we'll see, there are different kinds of streams as well. That doesn't always fit very well into this paradigm. But back pressure is a key concept in the spec.
So back pressure actually is, I would say, even the key concept of this specification because, well, it's easy to have interfaces defining a consumer and a publisher contract, and you interact with the method on the consumer from a publisher perspective. But the real innovation of this specification is the flow control mechanism. It's a kind of reverse flow where the consumer can say, I want more, or I'm not ready to accept more events. And if you think about that, if you have a way to say to a publisher, to an emitting sequence of whatever, that you're not ready to accept, well, if you have a queue in the middle, for instance, this queue is not going to overfill because at first you didn't have the event flowing in because you didn't ask for this data at first. So that's a kind of active back pressure where you ask for more, and if you don't ask for more, you're not receiving it. So that's really, really interesting. In terms of API, it's quite simple. So first, it's implemented in Java. Actually, it's available on Maven as a jar. It's just providing 4 interfaces. There is also a jar called the TCK, which helps you verify actually you implement this interface well. But you see, the interfaces are quite simple. You have a publisher where the publisher is something you're going to attach, something that listens for data, what we call a subscriber. So publisher, subscriber, really, well, I think that talks to everyone. That's easy to implement, it looks like. And the subscriber has 4 methods. One is onSubscribe, which is the first method actually invoked to receive this contract. Actually define a sequence of a signal, and the first method is onSubscribe, and it passes to each subscriber subscribing what we call a subscription, something that keeps track of the number of elements the actual subscriber wants to receive. And we have also on next, on error, and on complete. So these 3 methods are actually defining the message received by the subscriber, and eventually, if there is a mistake, a failure, also, well, the callback for the error, it's going to be directly on error. So that's interesting because that means in this spec, when you start implementing these interfaces, you can raise exceptions. The exceptions are never going to be, well, except for some cases, they are never going to be bubbled up to the publisher. They have to be passed as a subscriber. So for instance, you have an onNext method in a subscriber failing, like null pointer exception in onNext. It's not going to be actually the publisher who's going to receive this exception. Well, it might wrap the exception, but it's going to delegate that to the onError method of the same subscriber. So you can see what we call here failure tolerance or isolation from the publisher perspective. The publisher is not going to receive this exception, so it can keep sending on next message or subscribe new subscriber. But the specific subscriber who failed with a null pointer exception have received an error callback.
So if you just think about the publish and subscribe, there would be a single arrow going from left to right, and publisher is giving things to the subscriber. All that's happening here is providing a mechanism to reverse that relationship and to allow the subscriber to basically give the subscriber a subscription, and then that subscription can be used to make requests. So now it's the subscriber, if at all possible, the subscriber, well, the spec mandates it basically, but we'll talk about different kinds of streams. The subscriber is now in the driver's seat. It's asking for more items to be passed or saying cancel, and the publisher has the ability to pass data, that's the onNext method, or to pass on-error, on-complete signals, and that should be familiar from even things like Java Feature. So now we have a little animation going.
So yeah, we try hard to we tried hard to have a kind of animation, but anyway, Google Slides are quite hard to handle. So let's picture that exactly what happens in a flow between a publisher and a subscriber in this context of specification. So first, you have a publisher object and a subscriber object. They implement both the interfaces. Whatever they do behind, we don't care for now. Then the first thing you want to do, obviously, is attach this subscriber to a publisher. So you're going to call the subscribe method from the publisher, passing the subscriber. And then once you have attached to a publisher, what the publisher will often do, it would prepare a set of data, maybe pre-fetch a set of data ready to be passed to the subscriber. So think about a query for a database. If you attach a new subscriber to a publisher which is decorating a query, it's going maybe to start filling the queue in between, the buffer in between, with some result. So it's going to start doing a select, where, et cetera, from 0.5 because we have 5 slots available. It's not going to do more because we don't want to overflow this queue. It's going to select the 5 first results. And that's interesting because if we then attach the subscriber with this information, which we call subscription, the subscription is actually where we expose the request method. Request is actually the question. Well, it's not a question, it's an affirmation. I can accept more. Can you send me more data if you want to? Since the publisher has pre-filled this buffer.
What's the 0 at the top?
Oh yeah, and the 0 at the top is actually the pending demand. So at first, when you start attaching a subscription, you have asked nothing. You haven't called the request method. So the tracked number of I want this number of data, this number of objects is 0 because you haven't called request basically.
Then it should change, yeah. So we make a request.
Then we just accepted an onSubscribe method. We receive subscription and we call request 2. That means we upgraded to 2 pending requests. And we start emitting then the event because only now we know that the subscriber is ready to accept events. And you see the first event is poll, actually. It's not necessarily poll versus push. We see there are different mechanisms. As long as you have pending demand.
And that's one left.
Yeah, as long as you have pending demand, you can actually poll. So you have received the 2 first elements. And then maybe your subscriber, after the 2 first elements, will want to receive more. But because, you can track with different strategy, like you can time track and see, okay, those 2 elements, they came actually in less than 1 microsecond or 1 millisecond. So maybe now I'm going to spin up a bit and request more data. Instead of 2, I'm going to start requesting 5 by 5. And there are only 3 elements left, basically. So what does that mean is we're going to take all the elements left until there is nothing. But if there was something else at some point later in the future, it wouldn't need an additional request actually to get this data because we know actually we have 2 pending demand from the subscriber. So if anything new comes in the publisher, he knows that he actually can call onNext directly. He doesn't have to buffer. He can call onNext directly. And then eventually, it's not necessary, You can call the onComplete method, which is a limit to think about, well, you have fetch all results from database, basically. You are finished with that. You can call onComplete, but it's not really a requirement. You can have an unbounded or infinite stream of data, like, I don't know, trade data, for instance, or live stream or WebSocket. So the specification comes with a set of rules, and that's what makes the thing a bit more fun, actually, because implementing 4 interfaces with 4 methods or 1 method is quite easy. Everyone can do that in Java. But remember, the spec comes with a TCK, and the TCK is not really forgiving, actually. It will test if you have a real proper publisher or real proper subscriber. And doing so, it will pass a list of rules that are actually defined on the Reactive Stream site and GitHub. And some of them are quite restrictive. For instance, the first one, or one of the first one, you can call multiple onNext at the same time, or a non-subscribe and an onNext at the same time. So basically, no concurrent call to subscriber. So you might think, it's quite limiting. I mean, how does it scale up? We'll see that later, but that gives you a very nice protection from a subscriber perspective. That gives you the ability to access mutable states in your subscriber in a super safe way, because only one call at a time is actually, only one thread at a time is going to be into your subscriber. So basically, in your subscriber, you can have properties, mutable properties, in a safe way. You know that they're not going to be concurrently updated unless you do, your own stuff with asynchronous, I don't know, timer, for instance, into your subscriber. But that's your own, your own issue then. But by specification, the publisher is never going to invoke concurrently multiple methods.
And then there's the fun recursion issue.
And then there is a fun recursion issue, actually. Remember, we have this flow when first we request data, we receive multiple onNext call, and then we ask for more data, so we call again a request. But if we started requesting an onSubscribe, and then we go back having this onNext call, and then request more data, you can see at some point the stack is going to increase quite quickly.
Yeah, if anybody's worked with any sort of non-blocking API, you probably ran into this at some point, that there's a sort of a recursive situation that can easily occur with the subscriber asking for more data and then the publisher giving more data. And if you do all of this in a single thread, you're basically going to end up with endless recursion if you continue to ask for more things. And that's one thing that the spec basically says, that the publisher needs to cut it off.
Yes.
Don't allow too many of these. In other words, there needs to be some kind of strategy in place for dealing with that
and
sort of thing.
That's quite difficult, actually, sometimes to implement, to be honest. Passing the specification is not really an easy task, specifically around this issue. And also, it's been a few minutes we're talking about request, and we request for more data. But what does it mean exactly, the request size? It's not really bound to an absolute number of things you want to receive, so typically number of bytes. It's actually a score, a relative score you want to give to a publisher to say, okay, for this context, n is going to be the number of objects I want to receive. In some other context, and we'll see that specifically in I/O context, more about that on Thursday, it doesn't mean exactly the same thing, because we're not asking for a number of bytes, we're asking for a number of items we want to receive. And there is also a few exceptions. There are a few exceptions to this rule. We can also request infinite amount of data, which means basically we don't want back pressure. So this magic number is long max. If we request long max, the publisher knows that it doesn't have to wait for other requests to send more data. So it's pushing, and that's it. And knowing that we know the publisher won't publish until it receives request, there are multiple strategies of requesting, which actually are back pressure strategy in the end. The first one, the most common one, is stop and wait, which means we request 2, and after 2, we'll request 2 more, So basically, it's akin to acknowledgement at this stage. If we just wait for another request to request more, if we wait for exact number of items to request the same number of items, you see it's kind of acknowledgement mechanism. With 2 received, we want 2 more. 2 received, we want 2 more. But that introduces in your system a kind of micro-pause, because maybe the time of requesting, the process of requesting is a bit expensive. So, and this time could be used to prefetch data, for instance. But the publisher doesn't know that. It will wait for the request to fetch more data. And that's, well, stop and wait. So it's good for acknowledgement and kind of delimitation like that. But if you want more performances, the second strategy comes in, which is prefetch, basically. It's not new. A lot of technologies implement this kind of behavior. The publisher can preload a set of data, and actually that was the example in the sequence diagram before. We can ask for more data than actually the subscriber wants, but we're not going to pass to the subscribers this data, because remember, as long as he doesn't request this data, it shouldn't receive this data. But maybe we can pre-cache them, because we know at some point he will request this data anyway. So that's what we call prefetching.
And I guess if you've been working with any kind of messaging systems and solutions in the past, you kind of probably, this might be familiar territory. That's the kind of the domain of those things. But now we're talking about this becoming message passing in an event-driven architecture within an application.
It's completely agnostic, actually.
So it's basically a lot of the same questions and same strategies.
Yes, if you think, for instance, about RabbitMQ, RabbitMQ has a prefetch strategy. What means prefetch in RabbitMQ? It just means even before the consumer is ready to accept more data, RabbitMQ is going to send n number of items to the client. So the next time he requests data, it's already here. That's exactly the same.
Okay, so we come to one demo, our first demo. And for that, I'm going to take out what we have here. So basically what we have here is an implementation of a publisher. And what we wanted to show is that it's quite easy to take these interfaces and implement them, and what happens as a result. So basically what we have here is a publisher being created, and it's going to take a list of integers. And then when we have a subscriber, we're simply going to iterate and give those items from that list to the subscriber each time the subscriber requests. So we have a contract, we implement it and see what happens. And then at the same time we have a subscriber, and then here is the subscriber, which when the subscriber receives a subscription, that means we're ready to start asking for items, and we're just going to request one initially. And then each time we get one, we're going to ask for another one. So we're just processing one item at a time. So let's go ahead and run one of these. Let's say with 10 items, and then we're going to subscribe, and we're going to create our subscriber.
There is an interesting property also you might notice. The subscriber has its own iterator. That means that if you subscribe twice, the observed sequence from the subscriber is going to start again from 0, basically. And that's interesting because that's what we will call later a call data source, something that you can replay.
So we basically got all the 10 items, and then we got the on-complete signal. So it looks like we're successful. Now what we will take a look at is basically a implementation of or use of the TCK. So as Stefan mentioned, the contract or the spec comes with a TCK, and you can extend one of these classes to take a look whether your publisher is actually compliant with the spec. So we have here our naive publisher.
It's important to have this TCK because we have a few implementation around. We have AkaStream, we have RxJava 2 and the bridge with RxJava 1, etc., etc. So this communication between two different components is really about behavior, not specifically about the API, and we have to test that. Oops. And actually, you can see that implementing is not that easy.
All right, we're not done. So we have a number of failures, and we'll just take a look at some of them here. This one, actually probably just looking at the name, may signal less than requested and terminate subscription. Let's see one that's a little more interesting. Must allow synchronous request calls. After subscription is canceled, request must be no ops. So there's a whole bunch of things that obviously we're not compliant with. And the whole point of this exercise is to show that simply implementing the contracts doesn't necessarily make you a good citizen of those contracts. There's actually additional rules that you need to abide, and those cannot be expressed in the contracts alone. But this is why it comes with a TCK. And the second point is that this is not trivial stuff. I mean, this is not something that you want to implement from scratch. This is something for which you need infrastructure, something that would give you a foundation on which to work. And again, we're a little bit lower level than what applications are actually going to be implementing for the most part. This is the sort of thing that you need to understand, but maybe third-party libraries like Mongo and others will actually. Mongo has a Reactive Streams implementation, so. And there's a Couchbase talk later on today, which is on the same topic. So now we're going to go back to our demo. And this time, so we're done with one. So now we're going to take a look at the publisher factory. So this is another way we're going to create a publisher, and this actually gives us a little bit of infrastructure. This is coming from the Reactor project that Stefan leads. And as you can see here, instead of implementing publisher from scratch, we're basically using a publisher factory and then taking the subscriber as input and then basically simply producing items, and that's going to take care for us of all the rules. By the way, one of the important things on those fail tests, one of them was the recursive requirement. Because we did everything synchronously, we just naively published all the items. That leads you into the recursive relationship between publisher and subscriber. Let's take a look at the tests. So here we have another test. And if we do run that.
So, is it the publisher's responsibility to break the recursion?
Whose responsibility is to break the recursion? Yes, yes, it's the publisher's responsibility, generally speaking. Generally speaking, it's the publisher's responsibility, period. Not just for this, but in general for any of those issues. In other words, subscriber is expected to be something that you can implement just by implementing the contract, and it should just work. So the onus is on the publisher to take care of a lot of the heavy lifting for
that allows you basically to implement the subscriber directly and start requesting without thinking about all this stuff. There are a few rules like input exception if there is a null pointer exception, but that's the only thing you should take care as a subscriber. The publisher will take care about the unbounded recursion, for instance.
Okay, this is pass, and it's probably too small to see, but there are certain ones which are
optional.
They're optional. They're basically stuff that cannot be tested very easily. So there are some spec rules which are not explicitly tested in the TCK. Okay, so now that we've seen this, let's try one more thing here. Okay, so let's actually try a little bit of the back pressure. First of all, let's switch to the publisher factory. And now if you go into the subscriber, well, the first thing you might think about doing is just taking out our initial request, see what happens.
What will happen then if you don't request initially? In theory, nothing. If you don't request for data, well, you don't request for data. So.
Yeah, so we didn't get anything.
But that's a form of back pressure as well. I mean, if you didn't request data, you didn't request data. So the publisher knows he can't send data anyway.
So let's request 5 and then take out the one that's down here. So initially we request 5 and then we stop requesting. And for that, we get 5 items and we exit. We never even get on complete because the stream didn't finish. We just never ask for more, and then we exit it. So that gives you an idea about the back pressure. The requesting part. Now let's, for the fun of it, do the naive publisher. And shall we try 10,000? So we need to change the subscriber again.
Yes, it's still requesting only one.
Let's keep asking.
Yeah, specifically, you see, when you implement the onNext, the unbounded recursion happens when in onNext you keep requesting one. And in that case, there are 10,000 data ready to be forwarded. So that means 10,000 times we're going to request.
That's 10,000 recursion. That's not working.
That's
too
what
well.
happens, basically Stack Overflow. And that a lot of, you see that if you do non-blocking and if you use a composition API, you have to take care of this kind of thing.
But with the Publisher Factory, we pass.
Yes.
So there's no
Because
there's
we
no
spent
recursion.
countless nights into making sure the unbounded recursion was not unbounded.
Yeah, and actually, just a little side note: there's no this is still a synchronous publisher.
Yeah.
There's no additional threads behind the scenes. It's more of a, what would you call it? Technique.
Yeah, it's
for basically
it's
detecting if you're getting into recursion, and then
it's quite simple actually. If we request to a publisher, we know that we're already inside this method when we on next. So the next on request inside the publisher is going to check if he's already publishing. If it's already publishing, it's going just to add up to the pending demand. So the current publishing method call is going to, yes?
So in your naive example,
Yeah.
or like what you talked about at the very, very beginning, the naive example, like you have a publisher that produces 1 million events,
Yeah.
and it fills up a queue with 1 million events because you have a slow consumer. And here, you're talking about, well, now your consumer has the power to say, well, only give me 5, only give me 10, only do whatever. But those 1 million events are super important data, and you don't want to lose it.
But you didn't.
Yeah.
But you didn't request for them at first.
Well, so you had an example here where you produced 10,000 events, and you only answered 5.
So the question is what to do with overflow, especially if those events keep coming, and that's something we're going to get to, fair to assume. So on the subject of asynchronous versus synchronous, we already touched on that actually, but basically it's the publisher's responsibility, generally speaking, to deal with these kinds of issues. The spec actually does allow publisher to there's specifically a section that talks about this, that you can do it synchronously. But basically it's the publisher that's difficult to implement because it has to deal with when should it be synchronous, when should it be asynchronous, preventing open recursion, ensuring that on next happens in a sequential manner, not concurrently. So that's something that publishers are responsible for. For JDK 9, so basically the important bit here is that reactive streams is actually going to be adopted in JDK 9. This is going to be part of Java util concurrent in the flow, in a class called flow.java. All these identical contracts are going to be in there. And you might be wondering why is this going into JDK 9 in the first place? There are a few links in the bottom, so you can actually read some of the discussions with Doug Lee's answers. But basically, it boils down to the fact that Java util concurrent, its purpose is to deal with asynchronicity and concurrency, but there's no single best API for async and parallel in Java. So we have the completable future, continuation style programming. We have the Java util stream, which is useful for things like collections. That's what it's best for, suited for pull style. But there's really nothing for push style API, which is exactly what Reactive Streams is dealing with. And I guess there have been requests from various places to have something like that in the JDK. So it's basically a natural alignment where it's like, yes, we want that. We want that in the JDK. And in terms of the details, there's the flow class, which will contain these contracts. Then you have a flow consume and a flow stream, which are simple bridges to Java 8 APIs. Most importantly, there's a submission publisher, which is an implementation, actually, of a publisher that's provided with the JDK. and that has quite a bit of sophistication, and it offers different strategies for actually pushing into the publisher, pushing data. So it's kind of a bridge between some kind of a hot source and reactive streams pipeline where you can pass events. And of course, if you have multiple subscribers, it has to deal with what happens if they cannot all take the data at that time. But that's really what it's about. Now, the integration with Java 9 is not very deep. I think it's coming fairly late in the cycle, so they're not doing any further things in JDK 9 with it. They're not integrating it with NIO. They're not integrating it with HTTP client for HTTP 2. But presumably all of that will come, and just putting it in the JDK, I guess, has a significance and has drawn a lot of attention from various libraries that build on the JDK. And for the second part of the talk, I guess we'll switch to talking about async composition. So hopefully this is where things are going to be a little bit more on the level that as developers we think about most often. So the question here is, if we have an application and that application is dealing with different kinds of things in the backend, HTTP data, maybe some kind of messaging solution, and all of that is exposed through a non-blocking API like asynchronous, like reactive streams. How do we actually compose logic? How do we put things together? I mean, you saw a little bit in the example how nested it becomes very quickly, and that's kind of the challenge there. That's the second part of the equation. So in order to work with streams, we now have services that are not returning data, they're returning publishers. Fundamentally, they're becoming non-blocking. This is really what it's about. So how do you attach further processing? Do you subscribe to that? And then when you get items, you start requesting and then pass them on to something else. That's a lot of work. That's not a very straightforward way to deal with this. And fundamentally, Reactive Streams doesn't aim to address this issue. Reactive Streams is purely concerned with interoperability among components developed by different vendors, different providers, but it's not concerned with how exactly you compose this. That's kind of expected to be solved as a separate problem. And we have stream, something called stream operations that we're thinking about here. Essentially, a publisher represents a stream of data, and you want to be able to apply some kind of operations on the data in functional style. If you're familiar with the Java 8 streams, that's roughly what we're looking at, what we're talking about. That's the kind of API that can put you a level above the callback. So you're not like physically subscribing to a publisher and then passing the data on to some other subscriber if you're in the middle of a chain. Right, so that's where we need something to provide us with these kinds of operators. And first thing we'll mention here is Reactive Stream, which provides a stream API. Essentially, you can think of it as a publisher, which is enhanced with further operations. So you can do things like define a stream out of 3 elements, and then you can say, I only want the first 2. Then you say, I want to map it to some other data type. And then at the end of that, I want to consume it. So that's kind of the general idea we're talking about. Now, if you were to implement that, bare bones reactive streams, obviously that would be a tremendous amount of code. And how it becomes condensed is just unbelievable to see if you try it first the other way. So let's do a demo of that quickly. So we can take this out there. So we have 10 items, and we're just going to do streams, which is kind of the factory for creating streams, and we're going to say
basically, it's using Publisher Factory. It's a separate module we have in Reactor, because Reactor is split into different modules. There is the message passing module, which is Reactor Core, and there is the composition module, which is a Reactor Stream. And Reactor Stream, of course, depends on Reactor Core. So this one is going to just delegate to a stream.
Now, I could have, I'm using here Java 8 Lambda. I could have, done it like this, and this is what we were talking about earlier with
features on languages, actually.
Feature of languages. So let's start from here because that's a little easier to understand. Consumer is just a simple function which accepts the items as they come available. And you might be wondering, where's the back pressure and all this? Well, we'll take a look at that actually in a moment. But let's first of all go ahead and run it. And we should get 10 items out of that. There we are. So now, working with Java 8, it's really easy with the IDE to get used to it. So you can see that this is grayed out, which means that we can replace it with a lambda. And then that's also telling us that we can further reduce this to a method reference. So this becomes very simple. You can see the language feature can help quite a bit to make this a little easier to read, because ultimately what's happening here is we're just taking an item and passing it to system out print line. And that's really what this is expressing. Now, in terms of what's happening here, let's use the log operator. So you're starting to get the idea. There's all kinds of nifty things available. And run that. And what you see here is that initially we're requesting long max value, which means that we want to consume everything that this stream has. And that's really what happens then. We just get 10 items. But we could also do something like this. We can say we want to consume 4 items at a time. That means we have a capacity in between in that pipeline.
Yeah,
we're going to be pulling 4 items at a time and then passing them down as we consume them.
Capacity is just an operation to say, for this given sequence of data, I want to limit the in-flight data to 4x4, for instance, in that case. So you can see it's going to directly translate as an information to consume operation. It's starting with 4, and after 4, it's going to request 4 more. So we limit the in-flight data to 4 at any time.
Yeah, and there's other things you can do here. You can also say, I want to consume it separately. That's the consume later. And take the return value, which is a control. And now you can say, control, give me 1. So you can do stuff like that as well. And you can see here we're getting only 1 item as a result of that.
It's mainly useful for testing operation, because one of the big issue can concern in this kind of architecture and programming paradigm is the testing. Testing asynchronous result is not the easiest way. So we need this kind of facility to, interact directly with the contract.
Now, another option here is reactive extensions, and this is something we haven't mentioned so far, but basically this is another composition API very much in the same space for composing asynchronous logic. And it's something that originated at Microsoft at .NET by Eric Meyer. And it's implemented in many languages, so it's polyglot. There are implementations available, so it's like patterns basically. What kinds of operators we have. You have RxJava at Netflix, RxJS, Rx.net. There's a whole bunch of them, and you can see that it looks very similar. The main thing is that you have an observable observer instead of publisher subscriber. So that's a slightly different terminology, but it's very much the same concepts. And RxJava version 1 was actually developed before Reactive Streams, and the developers at RxJava were part of Reactive Streams. So in fact, RxJava very much, there's a bridge, so you can adapt to the Reactive Streams API and pass the TCK tests and everything. Supports reactive pull back pressure. So it's very much in line with Reactive Streams, but the first version happened to be developed before it.
It's going to be fixed by...
and version 2 is going to be based natively on Reactive Streams. There's work going on that. Now, an interesting comparison actually is reactive extensions versus Java 8 Stream API. The Java 8 Stream API is built for collections. That's really what it's best suited for. And that means an iterator style. You're pulling items. While an observer is pretty much the same thing. It's just the inverse relationship where you're pushing items instead of pulling them. And that's important, again, back to why this is getting included in Java 9. Now, observable actually can be used to represent an iterator as well. As you saw, we actually created a a stream out of a collection, and the same can be done with
The difference is
observable.
it's not all of nothing or nothing like in a stream. With an iterator, you do on next, you do next, next, next. It's basically one by one, and you pull everything then. With a request and a demand information, if you have been asked for 5, you can send 5 data, for instance.
Right, so let's take a quick look at RxJava as well. And it's very much the same thing, but using observable. So we're going to use an observable from items, and then we're going to subscribe for that, and we can do a simple action. Well, okay, I can still do it the long way first. I can provide an action, and then I can say system out, print line.
You can feel there is a kind of, a standard
Integer.
about this thing, this kind of implementation.
But I can then
really feel the same.
replace it and do all the way back to this. So I'm just consuming items, just the same thing, basically.
Print that in.
Oh yeah, print line. This looks like max value.
Yes.
What's that? Right, so here we got everything. And there is actually a verification. So this is actually a TCK TCK extension of the TCK test for reactive streams. And what you'll see here is we're using an observable, but we're adapting it to a publisher. So that's the reactive streams bridge for RxJava. So RxJava is basically something that can be adapted to reactive streams, and that runs. And it's also possible to do logging here as well. You can do things like do on request, and you can probably just print that out. Let's at least say system out print line request a long. And you can see that what it's doing also by default, it's requesting long max value. It's consuming everything out of the box. So very much the same idea, the same concept. Now, obviously a question of RxJava reactor. Well, there's going to be a lot of libraries in this space for providing composition APIs. This is something that's going to be an application choice. At the moment, RxJava is more or less the de facto choice, I would say. It is for composition and applications. It has a very wide variety, a very rich choice of operators, which are implemented in multiple languages. So you have, RxJS, and then you have RxJava, so you can use the same concepts on the client side. It's really well documented. It's mature. So I would basically recommend that as the first place to take a look. Reactive Streams is actually quite well positioned for use in library APIs because it's more focused. And in general, libraries should not be tied to one composition API or another. So if you think about an underlying library like Mongo, they probably want to remain agnostic to what kind of composition is used above, because one application might choose RxJava, another one might use Akka Stream, another one might use Reactor Stream. There's no one answer. So for this reason, Reactor actually can be positioned well as a foundation for libraries, as well as for some high volume, more specialized applications for which it's used in production. It has a more focused set of operators, but it's natively implemented on reactive streams today. So that makes it attractive, and it provides infrastructure that you need anyway around reactive streams. So as a library, if you need to develop something around reactive streams, Reactor becomes an attractive choice because it's focused strictly on providing kind of infrastructure around reactive streams. This is the list of operators in Reactive X. That's actually taken from the website. As you can see, it's very long. There's a lot of things, but this is a little bit unfair. This is actually the true picture in RxJava. The previous list is the superset of all operators across all languages. And as you can imagine, when you have a pattern that has to deal with method names, they're not all named the same way in all languages. So sometimes there are variants. So this is the superset across all languages. But if you click on that link, that actually breaks it down pretty well. Now, what it boils down to is there's only so many things that you can do with sequences. You can originate sequences. You can produce one from a collection or a range of something. You can reduce them in some way to have a smaller sequence, maybe by filtering, maybe by aggregating, partitioning. You can transform them, combine them, or we can control things like overflow and errors, which was the question earlier, what to do when you have too many. And in order to take a look at something concrete, this is an example of how you might go from a blocking service layer to a non-blocking service layer where things that you were returning before were concrete, but now they're streams of things. Even for one thing, it's now has to be non-blocking. That's fundamentally what we're looking at. And
even if we go synchronous, actually, it's abstracting away the threading model behind. You'll find user might return a list of user directly using observable from, for instance. But at some point in the future, you might use another operator like observable.create, which will deal with lazily fetching the data from a database, for instance.
Yeah, we talked about being agnostic, basically. This allows you to be agnostic. The first one is basically a blocking service layer, while the second one is agnostic. It can be blocking, it can be non-blocking. So let's take a look at a demo. First, for the list of operators, we actually used RxJava to derive that. So let me take this out first. So what you'll see here is this is using RxJava to derive the operators in RxJava. And it's done by introspecting the observable. I think initially I started by doing some grepping on the command line and doing pipelining, with Unix pipes, and doing grep -v, and then wait, there's actually methods in observable. Can I use reflection? And then I started doing a for loop, and then wait, we can actually use a stream for that. So you can see here that we're taking the class and all the methods. And then for each method, we're doing a filtering where we're looking for the return value to be an observable. So those are the operators which return. That's the Fluent API. That's the chaining of the methods. Then we're simply getting the name of the method. We want to make sure any overloaded methods are collapsed. And then we're sorting that out. And that's how we get our list of operators. And what's interesting that you can do the same thing using Java 8 Stream. So you can see that we're actually extracting the same information. So there's a lot of overlap between the actual operators that Java 8 Stream API provides and RxJava provides and Reactive Stream. And actually, I think in version 2, they plan to support the Java 8 Stream API in addition. But what you can do with RxJava is much more than what you have in the Java 8 util. Stream. And there's a similar demo for Reactor Stream, so you can see that as well. Now, for the second part, we actually have a demo with something that you might see more like an application, which basically we have a Twitter, we have a LinkedIn service, which finds some users, kind of like Spring Social.
Another interesting fact, when you move from blocking imperative code to something that returns a deferred result, publisher, an observable, or whatever, is you don't see in the method signature throw exception. It's basically not like that now. You can't actually count on that because the exception will maybe happen in a different thread. And that's why the subscriber is the one responsible now for doing something with the exception.
So basically the goal here of this canned demo, like really simple stubbed example, is to the idea that we're going to find some LinkedIn users based on a skill, the reactive skill. Then we're going to take the first 5 of those. That's the take 5 operator. And then we're going to do something called flat map, which I'll get back to in a moment. But essentially what we're doing is we're taking the first 5 users that we search with the skill reactive. Then for each one of those, we're going to make another further calls to Twitter and Facebook because we want to get their profiles. And then we're going to collapse that information so that for each connection, we want Twitter, LinkedIn, and Facebook profile information data. So I can run this. And basically, we get this kind of collapsed information. The main person here is at the top, and then we have the connection, which is along with Twitter and Facebook information. So this is the kind of thing that we're talking about being able to solve. You're making non-blocking calls to services. Then you're taking that information back. Each one is a stream. How do you combine that? How do you send it back? How do you stream that through and through from end to end?
And if you really
that's the fundamental issue.
If you really think forward, what you're writing with this kind of code style is actually a real-time query over a set of data, basically. It's very easy to translate actually as a query. If you think about what we do, we just limit the number of data. We do a select, which is a map. We do filtering. We do sub-select, which is actually the case of flat map. So it's quite akin, and that's probably where more and more data frameworks even evolve.
Right. So if you were scared about that code, there's definitely a learning curve, and terminology like flat map. Is obviously pretty much everybody who's talked about it says that they're confused about it at first. I think some of it is maybe the terminology, but some of it is also the concepts behind it. But it's actually not a very complex thing to think about. I think it's easy to understand and start from the map operation. That's something that we can understand. It's basically a map is transforming one thing to another, from one type to another. But if you think about that function, well, there's nothing that prevents us from transforming from one type to an observable or a publisher of another type, right? That should be possible. Effectively, what we're talking about is here with the LinkedIn example, you have a LinkedIn user and you found some connections. Now, for each one of those connections, you're going to call another service. Well, that returns an observable as well. So that's what we're dealing with now, multiple streams. What do you do with those multiple streams? So it's actually, the answer is very simple. In this case, flat map means that we want to flatten those, we want to merge those back in. So fundamentally, this is map, which gives you multiple streams, and then merging of those streams back into a single stream so you can continue to operate on it. That's really what this means. And yes, it is a mental shift. It's going to require, I won't say that this is easy to look at, not for me at first, but trust me, with a little bit of time, it's actually possible to begin to adjust to doing things like that. And this is actually making it a lot easier. Fundamentally, what we're doing is changing in a big way.
Also, the interesting fact is when you transform data coming in, like a connection, a user into multiple connections, it's done in a non-blocking way. So you can keep accepting new data from the original sequence, but the merge is not going to sleep or block or wait until it's done. Basically, it will accumulate up to a number of parallel merge operation, but it's going to accumulate this observable backlog and start pulling from them without necessarily waiting. If the data is here, it's going to be pushed. If it's not here, well, it's fine. It's not going to block the CPU.
So we won't be able to cover, obviously there's a lot of operators, but there are actually some useful information. There's even a decision tree. We have a link to that on the RX Java wiki and the ReactiveX.io website. One thing, so coming back to earlier question about what to do when you have too many events. Well, I think it's useful to talk about stream types, which we can talk about cold or passive sources of data, as well as hot or active sources of data. Basically, with the cold, you have something like a file reading from a file or a database cursor. And that's something that you can redo for every subscriber. You can start from the top. You want to read a file, each subscriber we can start from the top. With the hot source, information keeps coming. There's nothing we can do to stop it. This could be mouse events or timer events. Timer events is actually very common, and that's not something that you can repeat. You can further downstream, you can use operators to kind of begin to change the nature of these sources. And in fact, you'll see it's not a clear-cut distinction. What if you do a merge of a hot and a cold stream? What do you call that? Is that I guess it is hot, but it's more changing characteristics.
It depends on the operation, but it's odd.
But there are, and we'll just mention them, but basically, if you have a hot source, the only thing that you can do is you can buffer, sample, or drop. And for that, there are operators that allow you to do sophisticated. So essentially, you can think of it as a source which continues to publish, and then you have to choose what to do with that. Do you drop? Do you take a few every so often?
That's the main limitation,
actually.
actually.
Buffer them if it's a bursty situation. Maybe you can handle it by buffering.
So that's actually the limitation of reactive streams. It's automatically resolving for you back pressure in the case of cold sources, but in the case of hot sources, you can't escape the need to actively operate on this stream of things. You need to say, I'm going to accept a buffer. I can drop as well, or I'm going to reduce the stream by selecting only a few elements every X second, for instance, but you have to take action. Reactive stream is not going to solve this issue.
Right. Okay, so we have a little bit more actually on stream composition. One of the interesting things that you might wonder about is how do these operators actually work? And we have a few slides on that. Essentially, when you say map or when you say filter or take, any of those operators, it's not actually performing that work. That's a declaration of something that will happen. So that's a deferred declaration of work to be done. And nothing actually gets done until a subscriber shows up. So that's when we actually trigger the whole thing and start producing the data. And underneath all that is the lift operator. That's what makes it happen. And lift is basically a function which decorates a subscriber. Essentially, in order to defer the application of these different functions, we can provide a function which will decorate a subscriber. And at the end, when there is an actual subscriber, each operator will decorate it so that when data passes through, the functions get applied.
From a publisher perspective, actually, it's going to become one subscriber.
Single subscriber, yeah. This might be a little bit not easy to visualize at the moment, but it's just trying to give you a sense for the mechanism behind this. Now, when there is an actual subscribe, the lift chain actually gets triggered, which means that the subscriber becomes decorated once for each operator there is. And at that point, the data can start flowing, and each operator starts applying operations on the data. And every subscriber out of the box is operating independently, which means that you have separate data pipelines. If you have 5 subscribers, each one is getting all that stuff passed down the data pipeline. And this is an important thing that you start thinking about when you actually work with these apps. You might say, why have multiple subscribers?
Well, if you think about scaling up, for instance, you might want different subscriber operating on different threads and operating in parallel, either in a publish-subscribe fashion, so you will need to share the data between the multiple subscriber, or maybe in a kind of walk queue pattern, one of them is going to interact and do, I don't know, I/O walk, for instance. So scale up basically is a reason.
Right, and then there's a way that you can actually get a shared data pipeline, so you can kind of alter that relationship. And for that, we have a demo, but I guess what we should do is we should turn to questions at this point. Mm-hmm. We have a few slides left that talk about concurrency and error handling. It's not a lot of slides, but I think it's something that you can also step through after this, and clearly we've covered a lot of ground already. So we'd rather give a chance for questions at this time. Yes?
So
Is the Spring Reactive project used in other Spring projects? We have some bridge technologies in XD, in Spring integration, for Spring MVC also. In Stomp, we're using the Reactor client. So there are definitely examples where it has found its way. But in terms of embracing Reactive, that's more of a major topic that's coming in Spring 5.
Yeah.
How much performance gain can be had? It's a tough question to answer, but a lot.
It depends. No, I suppose, well, the story is all about being asynchronous versus being synchronous. Sometimes there is a cost, it's not free to be asynchronous. So it's not a magic answer to everything. Sometimes it's going to be faster to just have a limited number of parallel connections open, doing stuff in parallel, and in a blocking way, and that's it. But if you do so, it's because you don't have an issue of concurrency, and that's the main thing solved by asynchronicity. You can, with asynchronicity, not necessarily go faster than being synchronous, but accept more incoming requests, which is interesting for the web case, the server case, the IoT case. If you can have more concurrency as an input, that's already a lot of things solved. But if you're talking about data pipeline, sometimes or often, actually, synchronous pipeline are going to be faster. That's a form of back pressure as well.
I would say that if you have that kind of problem where you really need this, you're probably already in that space and trying out stuff. Because those are problems that you can only solve by going in this direction. Otherwise, it's probably not something you want to do tomorrow. It's in what? In what? So the tools that we're talking about, the question is there any monitoring including? The tools that we're talking about here, they're programming tools that enable you to program asynchronous applications. These are very foundational things that monitoring is going to be another layer.
Yes, for instance, for RxJava, you have historics coming on top.
Yeah, there are things you can do to get it to print information, but not. I assume you mean monitoring in the sense of tools for.
It's not a stateful thing with, you can think like Spring XD. It's not an active data flow. It's very foundational. It happens.
But if you come to our second talk on Thursday, which is about web applications, you will see that you can take Tomcat or Jetty, you can build a reactive streams layer on top of that, and then you've got monitoring for those. So those are not mutually exclusive things. These are more APIs that we are looking at as being adopted and essential for doing non-blocking.
Yep.
All right, thanks very much. If anybody has any questions, feel free to find us or
Thank you.